Now we can do our calculations. 4 into 5 is 1 1/4. And then we have -5 minus -3 for the power of 10. Remember, we need to subtract the exponent, so be careful with all the negative signs. That comes out to be -5 plus 3, or 10 to the -2. And now we really do have moles per liter. Now we really do have molar hydroxide, a concentration of 1.25 times 10 to the -2 molar hydroxide. And now it would be legal to say that this equals the hydroxide concentration. Now we can label this with brackets because this is in molars, moles per liter. And now we can try to find the pOH. So we're focusing on 1.25 times 10 to the -2. Well, that would be bigger than 10 to the -2 and smaller than 10 to the -1. This is the biggest number in the inequality, so it has the smallest p. This was the smallest number in the inequality, so it has the biggest p. P of 10 to the -1, well, we just take the negative of the exponent. And this term in the middle is the pOH. How do I know this term in the middle is the pOH? Because this number does represent the hydroxide concentration. So we end up with a pOH that's between 1 and 2. One plus 13 is 14, and 2 plus 12 is 14. So that's how I got these numbers. We know that the pH is between 12 and 13. So that's our answer. A pH between 12 and 13. As we would have expected, we ended up with a basic solution because we ended up going past the equivalence point. We've added more than enough equivalence of base to cancel out all the acid and still have some base left over. So again, the key thing here is that in order to figure out the pOH, you have to remember that when people use the symbol pOH, that's just shorthand for the P of the hydroxide concentration. The way to find the pOH is to find the P of the hydroxide concentration, which means you need to use a number that's in moles per liter. You can't just use a number that's in moles. So let's review the issues that came up here. When you're working with a start-change-end table, it's legitimate to work with either moles or molarity. Start-change-end tables can work for either moles or for molarity, and you should just use whichever units are most convenient for the type of problem that you're working on. If you go back in the videos, you'll see that there were a couple examples where we did do start-change-end tables just in terms of molarity. But in most of the cases, we did the start-change-end table in terms of moles. And why was that? Because we had started by combining two different solutions. Well, when you're combining two different solutions, you can't just use the original concentrations from the original solutions. We can't. And so in this table here, we couldn't just use 0.1 molar for the acetic acid and 0.05 molar for the sodium hydroxide, because when we put the two solutions together, the volume is going to increase and the concentrations are going to change. So it would have been inconvenient to try to keep working with concentrations because the concentrations are not the same that we started with. I think that the most convenient thing to do when we are combining two solutions is to work in terms of moles. Because why is that more convenient? Because the number of moles doesn't change when we put these two solutions together. So for example, in the original pure acetic acid solution, when we just had the 1 milliliter of acetic acid, there was 0.0001 moles of acetic acid there. But then after we added this other solution, the number of moles of acetic acid didn't change. It was still 0.0001 moles of acetic acid, because that's just counting basically the number of molecules of acetic acid that there are. And similarly, the number of moles of sodium hydroxide didn't change when we combined the sodium hydroxide solution with the acid solution. So it was more convenient in this table to work in terms of moles, and this table was also in terms of moles. But then if we're going to do that, we need to remember that other types of calculations have to be done in terms of molarity. In particular, the pH is based on the molarity, and the pOH is based on the molarity. So we can't just use these numbers for moles to figure out the molarity. Instead, we have to change the number of moles into a concentration so that we can then find the pH or the pOH. Now, whenever you make a kind of careless mistake, like the student and I made in this tutoring session, you shouldn't just say, gee, I need to focus more. You should ask yourself, what habits or techniques could I adopt that would make me less likely to make that type of mistake? So let's ask ourselves, what habit or technique could the student and I have used during the tutoring session that would have made us less likely to make this kind of silly mistake and frustrating mistake that we made? Well, I think it's pretty obvious what the more important mistake that we made is. The important mistake that we made was, if you go back through the videos, you'll see whenever we did start, change, end tables, we were lazy and we didn't write the units in our start, change, end tables. That was a bad model that I was demonstrating during the tutoring session. All of the start, change, end tables that I put on the board, I didn't put in the units. Well, now you can see that I was lazy and mistaken to do that. I should have been taking the time to indicate, at least at some points in each table, what were the units that we were using in that table. If I had labeled that these were both in terms of moles, then I would have been much less likely to suddenly start thinking that this number represented a concentration. So I think that's the more important lesson to take from this little example here. When you're using a start, change, end table, because theoretically they could work for either concentrations or for the number of moles, you should always, at least at a couple of points in the table, indicate what units you're using. Does that seem reasonable? Well, that's a basic pH. We would expect that to be very basic, because now what's basically happening is we've added enough base to completely neutralize the acid, and then we've added even more base. So now we would be somewhere up here at a much higher pH, between 9 and 10. So when we have both a strong base and a weak base, at this point we're just going to say that the contribution of hydroxide from the strong base is probably going to far outweigh the contribution from the acetate. Just like we're not even paying any attention to the concentration of hydroxide from the water, right? The water is putting in 10 to the negative 7 hydroxide, but that's so much less than these numbers here that we can ignore it. Well, we can probably ignore the contribution from this acetate here as well. So we'll just focus on this concentration. So that would give us a pH that's around here. So, okay, so again, we had 4 different cases over here. All of them were a little bit different from each other. One thing that's important is to think about what are the species in solution? What are the reactive species? So going back to here, what were the ions that we had to pay attention to?
Just the hydronium and the acetate and the nitrogen.
So originally we just had acetate, and that just reacted with water to give us the hydronium in an equilibrium reaction. All right, and then thinking about this situation, what were the primary species?
We added a sodium.
Pardon?
There's also sodium left.
Sodium. Mm-hmm.
Sodium acetate.
Right.
Water and hydroxide a little bit, and then you also saw the original acid.
So I think maybe you're thinking about the right stuff. So to start here, we were combining the acetic acid with the sodium hydroxide. And after the hydroxide reacted with the acetic acid, the main reactive species we had the acetic acid and the acetate. So that's why we needed the Henderson-Hasselbalch equation here. You can kind of see that because we're in the buffer region. What's the reactive species that we ended up with here at the equivalence point?
The hydroxide?
At the equivalence point?
Oh wait, we didn't have any? We just had a little bit of acetate left.
That's right. So remember that we started with acetic acid and hydroxide. And those completely reacted with each other. We used up all the acetic acid and hydroxide reacting with each other. That's what the equivalence point means, that you've got equivalent amounts of acid and base. So they completely reacted with each other. all of the acetic acid turned into acetate. But then the acetate could react with the water to make us somewhat basic. So here the pH was above 7. And then what species did we end up with here that were important?
We had NaOH.
Yeah. Some of the sodium hydroxide was used up, neutralizing the acid. But then there was still plenty of sodium hydroxide left over, and that was much more important than any of this weak base that we had. So we just focused on this. So those were those different cases.